Okay. So the last is basically this last Friday, we started a deeper dive on Boolean operations, right? We started discussing some additional concepts about Boolean operations and optimization. The first thing that we talked about was the consensus theorem. I know it's been a while, so I will give you a 30-second overview of that. You can go through this detail later at home, but let me try to draw something here. Imagine you have one Boolean variable x, and you have its complement x prime. Okay, and you have something, and instead of using a variable, I'm going to use a shape like a circle and a square. So you have two other variables connected with x and its complement, and they're in an OR relation. Okay, still with me? And then in addition to that, you still have a term that contains the other two variables. Does that make sense now, folks? I am just using shapes. That means you could practically ignore this and just go with whatever was rest. So you can ignore the AND combination of the two shapes that you have been dealing with. This is exactly what the theorem says. If you look in terms of variables, xy plus x prime z. So basically you have y and z connected with true and complementary version of the same variable. So when it comes to taking an AND of these two variables, you could just let it go. Right? So this is the theorem, and this is literally the proof. Quite a few sentences of Boolean algebra. So this is a theorem, or this is a approach for optimization that is quite heavily used, as you'll see in the subsequent slides. I wanted to just remind you of that. And there is another dual form of this. This is basically you are taking OR of the ends. Hearing me? OR of the ends. So you're eventually taking an OR. There is oftentimes in Boolean algebra, there will be something analogous to each other. So there is an analogous dual form of this theorem, which does end of the ORs. So basically, this is OR of the ends, and this one is end of the ORs. So basically, if you come up with a theorem like this, quite often you'll see there will be a analogous version between end and OR, simply because of the nature of Boolean algebra. So anyways, how do you use it? So basically you have two variables, x and x prime. Let me also draw it here. You have x and x prime. You have another variable in an OR relationship with this same variable. So instead of variables, I'm gonna use shapes. So circle and sorry, circle and my goodness. So you have x plus a circle, and then x prime plus a shape square. And then you have basically an OR combination of these two shapes. And then they are in an AND relationship with each other, which practically means you can get rid of this term. As simple as that. Okay, so you get used to it as you use it more often. Now, moving forward, I'm going to talk about some specific steps that people take for simplifying or optimizing. So basically, they go hand in hand. When you optimize, you basically simplify the Boolean function. And if you don't remember why, we saw some examples in the last lecture. When you simplify a Boolean function, the hardware expression for the same function will be simplified. So you will require less component. And I told you, in a field where you deal with billions and trillions in numbers, 10% reduction is huge, right? It's unbelievable. So that's why Boolean simplification is a very important step. What you are learning now over the next few slides, in fact, throughout this lecture, is, and as the name suggests, algebraic simplification. So there are different kinds of simplification, even geometric simplification, by the way. We'll talk about it. But algebraic simplification is probably the ground plane for simplification. So this is where you start. And I hope through my lectures, and that's how I'm trying to structure my lectures, you will see gradually that, oh, I hate this approach. And you go to approach B. Oh, I mean, it's better, but I still hate it. then you go to approach C. So you gradually start liking it, and then you'll see the value of why people spent decades trying to come up with new ways to optimize and better optimize and take this route. So this is where things started. So without learning this, you cannot honestly learn the other steps. So we have to start here. Still with me? All right. So there are I have something in mind already, and I hope some of you point it out as I go through this process. If not, then don't worry. I'll try to point it out after we go through these steps. There are a few steps that people follow. First step. So given a Boolean function, so I give you a random Boolean function, f equals ABC, DEF, blah, 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 right? You try to simplify it. First of all, you may not be able to simplify. It may already be in the simplified form, but you still give it a shot to see whether you can do something to reduce it further. Okay, that's the first thing we do. And the first step that we typically take is combining different terms. I'm going to provide specific examples as to what I mean by that. And eventually we'll also do an exercise together. And then you'll see how all of these come together in a real scenario. All right, so imagine this is your Boolean function. What we mean by combining terms is, notice you have some common items. You have A, D prime, and B common between these two terms. Can you see that, folks? So if I take A, B, and D prime as common, you're left with C prime plus C. Can anybody tell me what C prime plus C means? One, remember the very fundamental concepts, Boolean logic functions that we talked about. So OR of any variable with its complement is always going to be 1. So this is 1. And if it is 1, anything times 1 in terms of n formation is just that thing. So you're left with AB D prime. Still with me? Okay. So notice instead of 2 terms, okay, let's take a moment to appreciate what we have achieved by doing this simple algebraic step, like Boolean algebraic, not regular algebraic, by the way. So notice how many and how many OR gates would I have required to implement this? Can anybody tell me? We did this exercise in the last class, if you remember. Thank you. Yes, to implement this, you need an AND gate with 4 inputs. And then for this, you need an AND gate with 4 inputs. I mean, if you are using 4 inputs, if you are using 2 input AND gate, then you'll need 2 of them, right? 2 and 2. Anyways, so and then you take the output of both of them and OR it together for this. Okay, but now after you simplify, all you need is a 3 input AND gate. Done. Isn't that beautiful? You see that? That's what I mean by simplification. That's what you can achieve. And with just literally 2 terms, you could achieve so much improvement. Imagine what you could do with like a really high level processor level expression. Okay, next, let's move to the next one. Eliminating terms. First of all, we combined multiple terms into one. And then also we are eliminating terms this way. So let's take a look at this example. Take a look at this theorem per se. This is heavily used in Boolean optimization. X plus xy is practically x. And I don't have to tell you why. Let me show you. So if you take x as common, you have 1 plus y. What is 1 plus anything? Remember? 1. So practically you're left with x. This is often used for simplification like this one. What do you have in common? You have a prime and b in common. So basically, if you take a prime b in common, you get 1 plus c, which is essentially a prime b. So this is another one. You can eliminate term. But this is another slightly involved example that also uses consensus theorem, that the one that we just learned, to eliminate term. And this is a little bit, and I hope somebody asked this question, and let's do it. So let's try to implement consensus theorem here to basically reduce that form. How do I start? First, look for a variable and its complement. Okay, so I'm looking at a variable, say, let's see, BD. Let me mark it this way. C and C prime, I found it. I'm looking at 2 variables, C and its complement. And I see whatever is there with C, like C is connected to VD. And then C prime is connected to A prime B. Do you guys all see that? Any problem? So I've changed the order. I hope it's not confusing. So the first term is here, second term is here. Okay. All right. Now, what is this term, folks? Can I write it this way, that A prime B BD is practically this one? So doesn't matter if you have B, 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 it's practically just B. If you keep taking AND with the same variable with itself, you're going to get the same variable, right? So doesn't, I could just show it as two B's. That means you are taking an AND of these two terms. So is it in the form of consensus theorem now, the one that we just saw? So can I get rid of this term altogether? So I'm left with basically the first two terms. So I can get rid of the third one. Basically, I can get rid of the third term based on consensus theorem. Do you have any concern or questions or comments? Not yet. You'll see what I'm trying to, you know, or maybe let's not keep you waiting. What I'm trying to say, how do you know, right? I have the luxury of really curating these slides in a way that things will fall in place. Right? Things are going to work. I know that things are going to work. But in real life, when you're left with a function, Boolean function, how do you know which one will work? You try to apply consensus theorem, and then it doesn't work. Okay, sure. You try to take common items, it doesn't work. So how do you know that things will work out? That's the first question. So keep that in mind. We'll see that. Let's move to this next one. Eliminating literals. So what it means is, look at, this is another, looks simple, but this is another heavily used Boolean optimization approach, which is, remember this it this way. So you have one variable and you have a complement of the variable, and you have another variable connected to the complement of it in OR function. It means you could practically get rid of this literal, this, you know, extra variable. So you have x plus y. It looks simple, but let's do it quickly. Here you would have needed an AND gate and then an OR gate. So you needed two gates, AND and OR. To implement the simplified form, you just need an OR gate. Done. So simple. Okay, if you want to see the proof, I mean, this could be an interesting challenge. Try to prove this from this. Typically, this is an interesting way to talk about, you know, this optimization approach. So x plus x prime 1 y. If you try to prove this equals x plus y, it's a little bit challenging. You don't really know which term to bring in, but it's typically easier to prove the other way around, to prove that this guy, right hand side, equals to left hand side. I'll show you how. Let me show you. X plus y is the expression that you have on the right hand side. I'm gonna multiply it with x plus x prime. What is x plus x prime, folks? 1. And I take AND. Is that gonna change anything? Can I do it? Can I take an AND with 1 for anything? Yeah, it's gonna be exactly the same. So now when you multiply this thing, you get x plus x y plus, oh, sorry. I'm not erasing. Oh, come on. Sorry, the eraser, okay, for some reason it was acting weird. So I was gonna say x plus y and then x plus x prime. So you multiply x plus x y plus x prime x plus x prime y. All right, it's like simple multiplication. What is x? Quickly, not 1, it's x, right? X is x. What is x plus y? Is basically x y. What is x prime x? Can anybody tell me? 0. Yes. Plus x prime y. Okay. And now if I take x as common, I get 1 plus y plus x prime y. What is 1 plus y? 1. Yes. So you left it x plus x prime y. So I practically proved right hand side is equal to left hand side, not the other way around. This is typically easier. The other way around is basically you can just follow the opposite path. Yes. 1. Great question. So tell me something. Do you remember the truth table of OR gate? Let's see. ABF, OR gate. So you have 0, 0, 0, 1, 1, 0, 1, 1 as possible inputs, right? And OR is going to be 1 when you have at least one of the inputs being 1. So for all of these cases, this is going to be 1. And the only way it can be 0 if both of the inputs are 0. So now when you're taking OR of anything with another 1, that means you have at least one input that is 1. Do you agree? That means it's always going to be 1. There is no way it's going to be 0. Right? Okay, so all right. So apparently, this is an example which shows you how to use this strategy to basically reduce it. Now, I'm going to stop here, and I'm going to stop going through all of these steps, because I hope by now you know things are going to work, because these are chosen that way. I've chose this example in a way that, oh, this will definitely work. Things will fall in place. But if I just randomly give you this expression, do you know really which one to use? To use this approach, or to use the consensus theorem, or to use the other theorem? How do you know? You see that point? So rather than trying to just show you something that I know it's going to work, uh, I'm going to ask you to please go over this example at home and let me know if it doesn't make sense. Things will make sense. I tested them, obviously, right? And also, I just want to highlight the next step here. Adding redundant term is another strategy. All of these steps are basically strategies that we use to optimize things. And we don't necessarily need to use them in this order. As you see, it's not a rule per se. Oftentimes they work out, but it's not necessary that you have to absolutely use them in this order. Okay, and there is a chance that none of this will work for some functions. So you're just left with what you get, that's what you get. No more optimization. Okay, what do I mean by adding redundant terms? That's exactly what I did to prove this theorem, right? There was no x plus x prime, was there? I just basically brought it out of thin air to help me simplify or prove a point. So many a times it seems that when you add some terms, it helps simplify other terms. Okay, let me show you one example. Like, let's go through this. So this is a Boolean expression. I don't seem to understand how to reduce it, honestly, without bringing some random terms. So what we did here, and the side notes are also partly mentioned here, we just brought in an extra term, wz prime. You might be wondering, how can we just add a random extra term using consensus theorem? Remember, consensus theorem can go both way. So let's go back to consensus theorem. Notice, if you have 3 terms, you can bring it down to 2. But that also means from 2 terms, you could go the other way. Remember, every theorem that you're looking at, the Boolean theorems and expressions that you're looking at, they can be flipped. So from 3 terms, you can go to 2 terms, or 2 terms, you can go to 3 terms. You might be wondering why? Why would we go to the 3 terms from 2 terms? We are basically defeating the purpose. Turns out sometimes adding extra terms in one stage helps reduce other bigger terms. Am I making any sense here? Okay, so I should simultaneously make and not make sense. And I hope after at least after this example, some of you will realize why it shouldn't make sense, all right, to do it this way. But anyways, so what I did was I added an extra term based on consensus theorem. Okay, and let me show you what I used to add this extra term. Notice you have x and x prime, true and complementary form of the same variable. And w was connected to x, z prime was connected to x prime. So apparently I could just take these 2 terms, w, z prime, and add it, because it's essentially redundant. Okay? In an ideal world, I would have gotten rid of that extra term using this theorem, but now I'm adding this extra term using this theorem. So this is the extra term. But now that you have here, you can now take this w, z prime common. You guys all see that? You can take this w, z prime as common, and then you are left with what? Can anybody tell me? When you take w, z prime common, you are left with y prime plus 1. Make sense? What is 1 plus y prime? 1 plus anything is 1, as we just discussed. So this is gone. Make sense? All right. So now you're left with this guy, WZ prime. But now I can again replace WZ prime. Notice this carefully. Just look at these two terms again. The ones that I used to introduce WZ prime. I can use the exact same theorem again to now eliminate this term, don't you think? What it did was it came for a short while and helped eliminate this term with 3 inputs, which we don't like, obviously. The more inputs, the bigger the gates will be. So we eliminated this term, and then I eliminated the extra term as well using the same theorem. So basically just get rid of this. So you can manage to get rid of this extra term using the consensus theorem twice in the same expression. Okay, does that make sense to you now? Based on why? Okay, like I said, it should and should not make sense. First of all, it should make sense because things are working as I'm telling you. Because it is a curated example, obviously, it should work. But why do you think it shouldn't make sense? I think, how do I know that, like, I mean, isn't that random? Isn't that random? Like, if I give you an expression to all 90 of you, you'll probably approach this in 90 different ways. How do you know which term to add that will eventually reduce things down to, a simpler format? How do you know they are not just making things worse, right? Obviously, as human beings, we cannot take a brute force approach and try all possibilities. But you know who can? Computers. You're heading in the right direction. Yes, thank you. Yes, we can always write codes and handle. Obviously, do you think, these are simple examples, in a real life processor, which has so many logic gates, so many complicated Boolean expressions, we can take a manual approach like this? Probably not. Of course not, right? What we call, and I keep mentioning that, we use EDA, electronic design automation. And like I said, you cannot learn automation without learning the basics yourselves. Right? You have to write the codes. Computer doesn't know. Basically, you have to tell it what to do. Okay, do X, Y, Z. If it doesn't work out, just leave it as is, right? But keep trying these steps, the other steps, and the other steps. Yes. First step, this one, you mean? Oh, yeah, of course, yes. Sure. So notice you're given this Boolean expression, and we happen to notice, and again, this is, I admit that this is basically a little bit random. How do I know? We happen to notice that these terms, this one and this one, could be used to invoke the consensus theorem to create a term that will eventually eliminate this third term. Okay, how? Notice you have x and x prime, which is the true and complementary version of the variable. Okay, so remember the consensus theorem, x and x prime. If you have something with x and something else with x prime, you could add a redundant term like this. It's not going to change the output of the function. Okay, you could either get rid of this or you could keep it. So we generally get rid of this extra term, but for this particular example, we are introducing extra term. Okay, that's why it's called adding redundant terms. We know it's redundant, but we are still deliberately adding it temporarily. Okay, so what's going to be the redundant term here? X and x prime are your variables and its complement. So you're left with w and z prime. Does that make sense? So can I add w and z prime without changing the function output? Okay, so that's exactly what I did, w z prime. But now this wz prime is sitting right beside this other term, which was already there. Okay. Now, if I take wz prime as common, now we are dealing with these two terms, by the way. Well, if I take wz prime as common, you are left with y prime here, and you're left with 1 from this term. So 1 plus anything is just 1, and you just get rid of this 1. You're left with wz prime. But now, using the same theorem, which you use to create this term, we could just eliminate it. Like, okay, x and x prime, and you have w z prime with it. So w z prime is redundant. Let's just get rid of it. Done. So you just created it temporarily to help eliminate another term. It's not, yes. Great question. Great question. So, and I hope it will be answered after we finish this lecture. Okay. Okay, so when we design these Boolean functions, we don't really know the expression that we are going to end up with. So nobody wants to come up with a substandard or sub-optimized uh, expression. Of course, we just go with the flow. We just define the environments around us and the problem and the system that we are dealing with, and we are left with an expression. We cannot simplify and define simultaneously, because interestingly, here's the fun part. After you simplify, you cannot really directly relate this expression to something that is physically connected to real life. Things will make sense, don't worry. So for example, I'm trying to define some logic decision-making process for a car. And I keep using this example because we can all relate to it, I hope, right? Okay, if X, Y, Z, P, Q, R happens, then raise an alarm, something like that, okay? But if none of this happen, don't raise an alarm. Or if A happen, B doesn't happen, don't raise an alarm, something like that. There is a complicated decision tree. So as an engineer, you design the decision tree and you design the Boolean function according to it. You're left with an expression, but that expression is not optimized. You can then help optimize it using this algebra. And after you optimize, you can no longer relate it to the real life example, but it will work. It will give you the exact same output, but you don't know why. Okay, that's the beauty of math. Okay, great question. All right, so with these 4 steps, let's move forward and see another more complicated example where we will bring them together. And this is equally useless, but as the other examples. Why? Because this is curated, as you can imagine. I chose it in a way that things will work, and things will really nicely work. You'll be able to see all the functions working, things getting eliminated. You still have to learn it. There was a time when this was the only way. There was a time, and that time is long ago, as you can imagine, decades ago, many decades ago. It's no longer the case. We have much better tools and process and steps now. As I told you, as we keep going through steps, you think the other one was worse, and this is better, and there will be something better coming up. So without further ado, so this is a function. This is a Boolean function that you're left with, and you are trying to optimize it somehow. We happen to notice, and some of these are very obvious, especially when it comes to taking terms in common. Like this one, you have A prime, C prime, and D prime common between the two. So if you take this common, what are you left with, folks? B prime plus B. What's B prime plus B? 1. So basically, it will be eliminated. So you are combining these 2 terms to just 1. Simple example. Okay. Number 2. How about this? So there is a term called A prime B, C prime D. Okay? And this is A prime BD. So if I take A prime BD as common, I'm going to left with 1 plus C prime. This is what I'm going to be left with. So 1 plus anything is 1 again. So just get rid of this. You are left with A prime BD. And this is apparently gone. All right. And then in the next step, you can apply other theorems, like eventually consensus theorem. Like I said, as if these things are going to fall in place. And these are taken from the textbook, by the way, as you can imagine. The textbook obviously has to make a point and show you what it means by consensus theorem. It has to show you what it means by, adding redundant term. So these examples are curated by the textbook, and I took it from them. I didn't have to invent them myself, obviously. Are you still with me? Okay. So you can take a look at it or not, but I recommend at least go through it so that you understand what this step really means. I'm not expecting you to be able to know exactly, what steps will lead to the best optimized solution. Okay, because the more complicated the function becomes, the more stochastic the process will become, and you might end up with a different result than your friend. What if I started with consensus theorem and then took terms in common and blah blah blah? Remember, Boolean expressions can have multiple format as an output, depending on how you're optimizing it. And not all of them will be the best optimized case. Are you still with me? Don't give up, okay? If I stop making sense, please stop me and ask me questions, okay? What I'm trying to get to is, I hope when you think of optimization, we have this picture in mind. A function, you have a minima. This is your optimized point. This is probably the number of gates, the least number of gates, say. However, keep in mind a 3-dimensional situation where you have multiple minima. You don't necessarily need to have one minima, right? Do you see my point? Therefore, yes, Question? No. Okay, okay. So there might be multiple minima, like here and there. One could be local minima. You think it is optimized, but there is a better optimization available to other people, right? And that's pretty much the case. It's a very complex, multi-dimensional optimization process. And it's not as simple as just, okay, doing some Boolean algebra and be 100% sure. The way people become sure, and especially the simulation tools and optimization tools become sure that you have optimized the process, would be by comparing what? Can anybody, as an engineer, right? You have 1 million logic gates. You start like optimizing it. If you write a code, your code will be different from your friend's code because your code is essentially you thinking, but in a bigger way, handling multiple things repeatedly rather than you doing it manually, right? Right? So your code basically reflects you. Your friend's code will reflect your friend. So apparently you guys might end up with multiple different results and you don't know which one is optimized. How can I, as a customer, like maybe I'm buying this optimized hardware from you, judge that yours is better optimized than others? Can anybody give me an idea as an engineer? Yes. Yes, thank you. That's a good point. But for the most part, oftentimes that may not really reflect the right decision. Here is why. Okay. Is it same to have a 4-input AND gate versus like multiple 2-input AND gates? That's the philosophical question, right? It looks like you have 2 gates when you have 2-input AND gates. Here is what I mean. You have A, B, C, D. You could use a 4-input AND gate and just do it in one shot. Done. Or you could use multiple 2-input AND gates. First handle AB, and then do ABC, and then do ABCD, right? You could just do it in steps. So apparently it looks like the other approach uses more gates in terms of sheer number, but it doesn't always lead to the, in the end, we care about, it's way ahead, we are way ahead of ourselves, but I'm giving you a high level picture. It's important for you to understand. And the clearer, the sooner you have a clearer vision, the honestly, the better output you'll get out of this course and any other courses that you take. Things will make sense, I hope. So here is the thing. In the end, we want to sell things with minimum area and something that takes minimum energy to operate and something that works fast. So I'm giving you an area budget. Your design will have to fit in this budget. Somebody else's design will also have to fit in this budget. And there are different ways of putting logic gates in a way that despite them, maybe this guy takes 1, the other one takes 4, but they can fit 4 within the same area. There are techniques that people use. This is called layout design. Am I making sense? Like think of a drawer, like maybe I'm messy. I just put some random stuff and my drawer is all taken. But my friend is well organized and he or she can take more stuff and put it in the same size drawer because of efficient optimization, layout design. And that's what the engineers do. They can take more gates and put it in the same area. So that's why yes, this is an easy way for me to express. You're getting less gates. You're getting rid of 1 gate. Typically, that can lead to lower area. But simply because 2 approaches have slightly more gates versus the other doesn't always mean that it will have higher area. Because people have other optimization. They can optimize the layout. They can design the layout. They can have 3D integration, one on top of the other. So they can do tricks that others cannot. Okay, that's one. This is definitely a good answer, but it's not the full-fledged answer. The full-fledged answer is you care about the performance metrics. I'm going to just run. This is called benchmarking. I'm going to take your design. I'm going to run it. I'm going to see speed, energy, like how much power does it take to run a certain algorithm. Say I'm going to do factorization, say integer factorization algorithm, or I don't know, I'm going to run a dot product, like an AI step that are often used. Okay, and I'm going to see how long it takes to infer the model, something like that. So I have a standardized benchmark that I will run across multiple Boolean optimized hardware, and I'll see which one gives better result. And that's typically how we decide who did a better job at optimizing. In the end, honestly, it's difficult. Like I said, just the count will not always make sense, especially for more complicated situations. Like the way Samsung makes their transistors and their chips will not be the same as TSMC, will not be the same as Intel. They all have their own tricks and under the slips. So despite something looking like, oh, they have a smaller technology node, doesn't always mean they have the most optimists. So again, I don't want to get too digressed, but did I make any sense at all to you all? Okay, all right. So keep that in mind. So given a Boolean function, if I assign you a homework, which I plan to do to optimize a Boolean function, keep an open mind. Don't put a pressure on yourself that I have to come up with that exact expression that he's looking at. Okay, use your logic, try the steps that you learned, and try to optimize it as good as you can. Maybe you can compare it with your friends as well. And hey, did you come up with a way to optimize it even better? How many terms do you have? How many inputs do you have? And also remember, reducing input is a big deal. At some point, it will make sense. But instead of A, B, C, D, if you could do it A, B, C, it will make a lot of sense. Okay, all right. So I'm excited to show you this slide, which is gonna show you how we could arrive at a situation like this. How do we get these functions? Real life is not like the course that you're taking. When you go to office, say work for Intel or something, your boss is not going to come and give you a Boolean function. Just go and optimize it. Right? Does that make sense? So you encounter them as you design hardware. So here is a real life example, as I promised, as to how we can generate simple Boolean function looking at like a regular decision. So this is a sentence. The alarm will ring if and only if, like this represents exclusivity, like there is no other exception. The alarm switch is on and the door is not closed, or it is after 6 p.m. and the window is not closed. So basically this was the sentence. What we are learning to do is express our regular real life sentences into Boolean expressions, because that's where engineering comes. Okay. So first of all, what is your output? What is the decision? The decision is whether or not alarm will ring. So this is your output Z or F, whatever you want to use. Okay. So in the textbook, they used Z, which is fine. Okay. So this is your output. If Z equals 1, I understand that the ring will bell. Right? Alarm will ring. If Z equals 0, it will not ring. Okay. That's how I'm treating it this way. Okay. If the alarm switch is on, so I need a variable to represent the alarm switch. If let's take it as A. If A equals 0, that means alarm switch is off. If A equals 1, the alarm switch is off. Oh, on. Right? Does that make sense? I could use a variable I need a variable to represent the alarm switch. Is it on or off? Okay. And then I need a variable to see whether the door is closed or open. Still with me? Okay. I need a variable to see whether the time is before or after 6. If it is before 6, maybe 0. If it is after 6, maybe 1. And then I need a variable to see if the window is closed or open. Okay. So that's how you could represent most real life scenarios in variables, in Boolean variables with 2 states. That's important. Okay. I mean, it might be open or closed or half open. No, that's not what we can handle with Boolean. Then you have to break it down into smaller logic. Does that make sense? We cannot handle multiple decisions. Yeah, I might like Italian or, American food or Mediterranean. I mean, no, if you have multiple choice, it's either or. Typically for Boolean. If you have more choices, there are ways to break it down into 2 choices. We'll talk about it later. So let's see. Notice, just look for these keywords. And basically represents logical and. So if this is a variable A, you are taking an and of A and B prime. Okay, why B prime? Because the sentence spoke about the door is not closed. So it's emphasizing on the not part. So imagine we use a variable B that represents door open or close. So since we are emphasizing on not closed, we decided to use prime, AB prime. Or represents plus. These two are ended together. So you have C, D prime. Window is not closed. That's why D prime. Are you still with me? Okay, and don't worry, you will not have to in real life. You'll not have to read through sentences like this and do this manual labor to create this function. There are efficient ways to do it. And we're going to learn. And I told you, as we go through the process, Okay, it works, but it's not the best thing. I don't like it that much. So you'll see a better option. So there are better options, better approaches to making this functions using real life examples. But this is one approach. This is basically the most rudimentary approach that we're learning. So this is where we get serious. And this is practically the universal approach to making logic. Typically, when I was a student like you, like second year, I never took this that seriously. I never, hey, this is just another table, just come over. Okay, just move on. Done. But now I know this is practically the universal version of logic making. If you learn this approach, you could practically express any physical system into Boolean function without fail. And you don't have to deal with these sentences and or manual stuff. No, this is all structured, well-versed process. So should we take it very seriously? Shouldn't we? We should. Okay. I think you should know this at this stage. Not like years ahead when you oh, that was the point that works every time. So we will talk about two forms that we already, I think, spoke about: sum of product and product of sum. Remember that? And one of them, like especially this one, is typically universally used to come up with Boolean expressions. And we will learn this. And we have 3 minutes. I will at least show you this. And then if necessary, we can review this in the next class. All right. So bear with me. Imagine we have 3 variables, A, B, C. And there, without any loss of generality. I could repeat it for 4. I could repeat it for 5 variables. You just have more rows. That's all. Right. So imagine you have 3 variables. With 3 variables, you have 8 possible combinations with zeros and ones. That's universal, no exception. You have 0, 0, 0, 0, 0, 1, blah, 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 ending at 1, 1, 1. That's exactly how things are for 3 variables. Okay, now this is a function that you can define. This is random. We don't know the output. But given, considering that I give you this function, okay, if you have 000, you're going to have 1. If you have 010, you're going to have 1. Something like that. I tell you how the function should be. And I tell you this based on my real life system that I'm trying to portray. I'll show you how that is portrayed later on. But I'm trying to portray a real life system. And this function outputs will help me do it. But now, once you have this function, all you have to look for is the entries with 1. Just look for the entries with 1. Ignore the zeros. Still with me? Okay. So look for 1 and look at the variables. If you have 0, you take the complementary form of the corresponding variable. If you have 1, you take the direct variable. So tell me, when will you have function output 1? If A becomes 0, B becomes 1, and C becomes 1. Does that make sense? This is one option. Or I could also have 1 if A becomes 1, B becomes 0, and C becomes 0. Do you see what I'm doing here? Or I could have output 1 if A becomes 1, B becomes 0, and C becomes 1. Or I could have a function equals 1 if A equals 1, B equals 1, and C equals 0. Finally, there is another option. I could have function equals 1 if all of them are 1, A, B, C. See, I'm mentioning or. So that means basically all of this should be in an or relation with each other. Does that make sense? So this is essentially the function that you see here, which represents this truth table. So you have a random truth table, but you can create a Boolean function like this, just looking at the truth table. I don't need to give you the sentences and other things, all right? So this is what we are heading at. We are out of time, so I'll stop here. I'll review it in the next class, all right? Thank you.